This video is for lesson 18-1, Similarity Criteria. We're starting an activity about similar triangles, and the learning goals are to develop criteria for determining if triangles are similar, and also to prove one of the criterion called AA, or angle-angle. Let's start by writing out what the angle-angle similarity postulate would say. Just think of the name angle-angle. What do you think that would be in a sentence? I'll pause the video for you to write that. Here is one way you might write out the angle-angle similarity postulate. If two angles of a triangle are congruent to two angles of another triangle, then the triangles are similar. So here is a way to decide if two triangles are similar. What you're looking for is, are two of the angles of one of the triangles congruent to two of the angles of the other triangle? And if so, then we know that the triangles are similar. They're the same shape. They might not be the same size, but we would know that they're the same shape. Now here's a check your understanding question to test whether we're able to use this angle-angle similarity idea. Write whether angle-angle similarity can be used to show that the pair of triangles are similar and explain our answer. So there's actually two questions. Let's work question A together and then you can try question B on your own. In question A, we have a triangle. One angle is 110 degrees, another angle is 45 degrees. Because all three angles in any triangle add up to 180 degrees, we can figure out that this unknown angle is 25 degrees. 110 plus 45 is 155, and 155 plus 25 is 180. Are these triangles similar? Well, to use angle-angle similarity, we would have to have a pair of angles in one of the triangles be congruent to a pair of angles in the other triangle, and we do not. So this answer is no. These are not similar because of angle-angle similarity. Now I'll pause the video for you to try question B. In question B, this time we're going to answer yes, these are similar triangles. Because all angles add up to 180, if we have a 90 and a 35, we can figure out that the missing angle is 55 degrees. And so in the first triangle, we have a 90 degree and a 55 degree angle. In the other triangle, we have a 90 degree and a 55 degree angle. So we have similar triangles because of angle-angle similarity. One of the learning goals for this section was to prove that angle-angle similarity actually works. So to do that, let's take a look at this picture. We have a smaller triangle and a larger triangle. They look the same shape. And we're given some angles. There's a single loop in angle A and a single loop in angle B. Those are congruent. And then we're told that angle B is congruent to angle E. If you focus your attention on only one of the triangles and you look at what's labeled with the loops, we have an angle, and then over here we have another angle, hence the name angle-angle similarity. Now take a look at question B. Based on the definition of similarity, explain whether transformations can show that the triangles are similar. Well, these are not the same size, so we would need a dilation where we multiply by a particular scale factor to increase the size of the first triangle until it's the same as the second triangle. We could do that. That would take a dilation. And then these triangles are not in the same location, so we would need a translation to the right to slide the first triangle onto the second triangle. We could do that as well. So we can show that these are similar because a dilation followed by a translation would map triangle ABC onto DEF. And that's our proof that angle-angle similarity works. Next, in a previous activity, we learned that there were 6 criteria to show that triangles are congruent. You probably remember the names of those. There were SSS, SAS, ASA, and so on. So it seems logical that there's other criteria for showing that triangles are similar besides only the angle-angle similarity postulate. So is there an SAS similarity criterion? State what you think the side angle side criterion would say. So in question B, let's write out an SAS criterion for similarity, not for congruence. The statement might look like this. If two sides of a triangle are proportional to two sides of another triangle, and the included angles are congruent, then the triangles are similar. Next, we have an example problem to illustrate what that complicated sentence is talking about. We have triangle ABC, and we have these measurements known, and then triangle DEF with these measurements. Notice when you look at the side lengths that triangle ABC appears to be twice as large as DEF. I'm going to draw this situation. First triangle ABC, and then let's look at the smaller triangle called DEF. I'm going to try to draw it the same shape as that first one. So this situation is what that sentence is talking about that we had. Two sides of the first triangle are proportional to two sides in the second triangle. Proportional means that you would multiply this number and this number by the same scale factor to create that number and that number. In this case, that scale factor is 1/2. 4 times 1/2 makes 2, and 6 times 1/2 makes 3. There's a consistent scale factor that you can times both of those sides by to create these two sides. That means that they're proportional. And notice as well that the included angles are congruent. That was the other piece in our sentence. So it's this situation that's referred to by SAS similarity. There was an SSS congruence criterion in an earlier chapter. Is there an SSS similarity criterion? And if so, what do you think it would say? So I'm going to pause the video for you to write out what you think the SSS similarity criterion would say. Maybe you wrote something like this. If 3 sides of a triangle are proportional to the 3 sides of another triangle, then the triangles are similar. The sample problem here illustrates the case of having two triangles, knowing how long the sides are, and then in another triangle having measurements of the sides, and then having to decide if these are all proportional. Is triangle ABC congruent to DEF? To know this, we would need to know, are all 3 sides proportional? And we would need to compare corresponding sides to see if there's a consistent scale factor. So when we compare the AB to the DE, what is the scale factor? So like 6 times K equals 9. K equals 9 divided by 6. If you reduce this, this is 1.5. Is 1.5 the scale factor every time? So now let's compare BC to EF. So 8 times what equals 12? Well, let's divide by 8. So 12 divided by 8. And that's 1.5. Let's compare for the third sides, the CA and the FD. 10 times what scale factor equals 15? Divide both sides by 10. 15 divided by 10 is also 1.5. So these are similar because of the SSS similarity postulate. All 3 sides are proportional to the 3 sides in the other triangle. Let's work on number 7. For each pair of triangles, write the similarity criterion, if any, that can be used to show that they're similar. So we have this large triangle and this small triangle. We have these 38-degree angles, and we know some sides. So we have a side, an angle, and then a side. Over here we have a side, an angle, and then a side. We're thinking it might be SAS, but you can't just conclude it's yes because it looks like things are written in the right spot. You need to actually use what the theorem says. Are the sides proportional? So what's the connection between the 18 and the 9? 18 is twice 9. What's the connection between the 10 and the 5? 10 is twice the 5. So there is a consistent scale factor. We would say yes, these are similar because of the SAS similarity theorem. Please try question B and question C on your own. For question B, the answer is yes, these are similar because of SAS. We have a side, an angle, and a side, so we're thinking it's probably SAS, but we need to actually figure out, are the sides proportional? So is 9 divided by 6 the same thing as 9 divided by 6? And certainly it is. Now in question C, we need to answer this one, no, these are not similar. We have a side, we have another side, we have an angle. Over here we have the side, and we have the other side, and we have the angle. Notice that this time, even though the angles are the same, that angle is not an included angle. And furthermore, the sides that have marks on them are not proportional. What I mean by that is 21 over 14 is not going to be equal to this side over this side if these things are congruent to each other. Next, there's a couple check your understanding questions. I'm going to pause the video for you to answer these yes or no questions. Okay, number 8, are all right isosceles triangles similar? The answer is yes. Here's an example picture of a right isosceles triangle. That's a right angle, and that side are equal to each other. That's what makes it isosceles. Now look at another right isosceles triangle. Here's a right angle, that side are equal to each other. That's isosceles. These are going to be the same shape because of SAS. Number 9, are all equilateral triangles similar? And that answer is yes as well. Here's an example picture of an equilateral triangle. All 3 sides are equal. Here's another equilateral triangle. All 3 sides are equal. And I think you'd agree that no matter how many of these I draw, that these will be similar because of the SSS similarity postulate. Okay, that concludes lesson 18-1. We figured out some ways to tell if triangles are similar, and we then used those similarity postulates and theorems to solve some problems.